How do you correlate experimental vibration modes with Fey models? Imagine listening to a musical instrument and matching the sound patterns to the vibrations you see on a screen. That's similar to what engineers do when they compare experimental vibration modes with finite element models. It's a process that helps confirm if the computer simulation truly reflects real-world behavior. First, engineers perform experimental modal analysis by attaching sensors like accelerometers to the structure. They then excite the structure using impact hammers or shakers to measure how it vibrates naturally. This gives them data on the structure's natural frequencies, how it deforms during vibration, and damping characteristics. Next, they create a detailed finite element model of the same structure. This involves defining the shape, material properties, boundary conditions, and how mass is distributed. The goal is to match the physical setup as closely as possible. Once the model is ready, they run a modal analysis on the computer to predict the natural frequencies and mode shapes. Comparing these predicted mode shapes with the experimental ones is key. Engineers use a metric called the modal assurance criterion, which gives a number between 0 and 1. Values close to 1 mean the mode shapes are very similar, indicating a good correlation. They also compare the natural frequencies directly. Small differences are normal, but large gaps suggest the model needs refinement. If the frequencies don't match well, they update the model by adjusting material properties, boundary conditions, or mass distribution. This process is repeated until the predicted and measured modes align closely. It's important to remember that the system is assumed to behave linearly during testing, so nonlinear effects can make correlation more challenging. Properly representing the boundary conditions in the model is vital because constraints influence vibration modes significantly. Accurate mass and stiffness data are also essential for matching natural frequencies and mode shapes. Visual comparison of mode shape animations from both experiment and simulation helps verify the correlation. This process is used in many fields like aerospace, automotive, and mechanical engineering to validate designs, troubleshoot vibration issues, and improve product reliability. In essence, correlating experimental vibration modes with finite element models is about systematically comparing measured and predicted data, using tools like the modal assurance criterion, and refining the model until it accurately reflects the real structure's dynamic behavior.